Okay, on this second part of the video experiment we're going to make variations to the configuration and setup to see if we can change the type of discharge that we're getting from the fractal fern discharge to something else. So variations we're going to make, I'm going to try tuning up and down a little bit from the place that we currently are. We'll be using the vacuum variable capacitor here to do that tuning. We're going to be changing the blocking tank capacitor. At the moment we've got a 25 nanofarad 25 kilovolt capacitor connected at the output, and we are going to increase that to 30 microfarads at 8 kilovolts. So that's a very substantial difference, factor of 1,000 larger, which should change the blocking in the tank circuit considerably. We're also going to try different envelope from the power supply. So currently we are using the bridge rectifier for the first part of the experiment. So we've got a positive forward pressure out of the generator, and we're going to change that to a raw envelope with no blocking capacitor. So basically just the raw output from the high voltage transformers, and we will, as we're not using the rectifier or the semiconductors there, we can remove the blocking capacitor and just drive the coil system directly. We're also going to try putting a top load, a toroidal top load on top of the Tesla coil. That will obviously change its quite significantly its fundamental resonant frequency, series resonant frequency, and we'll see the effects of that. Also, we'll be using a different tube, so I will put the dual 833C tube board onto the heater grid screen tube supply. I've covered that in one of my other posts, and we will try driving it with a completely different tube from currently the GU5B. So those things combined together, we're going to see whether or not that fundamentally changes the type of discharge that we get. So we're looking for a change in the fractal-like nature, or a change in the fern-like nature, or something of the variation in the generator, power supply, the envelope, the drive envelope, the tube that's actually doing it, and also modifying the frequency, at least as far as we can realistically tune with the vacuum variable capacitor on the coil system. Okay, so also what I've set up here is I've added an oscilloscope on the top here with two traces. One is connected to a high voltage probe, differential probe, that's over the back here. Show that. That's the normal Pintec DP50 that I use, and that's measuring the output directly from the plate supply. So we see how much potential and the envelope of that generator output. I've also got, so that's the yellow trace, and that is currently set at 2 kilovolts per division. I've also got a Tektronix current probe here. This is a A6303 current probe. That's connected down to the Tektronix AM503B current probe amplifier, and then fed into channel 4 here on 50 ohm, and that's the red trace here. The current probe amplifier is set to 50 amps per division, and I've also bandwidth limited to 20 megahertz to stop interference with very high frequency noise. Okay, so that's the experimental setup. We will just do an initial run. So the coil system is currently set exactly where it was for the first part of the experiment. Tuning hasn't been changed. So currently it's tuned to about 231 picofarad with a vacuum variable capacitor. That's the point where I found the optimal running for the coil system, where it's smooth discharge, reliable, can sustain at CW for considerable periods of time, and also there is the currents feeding back from the coupling back through the secondary coil into the primary and into the tube are not too aggressive. Otherwise, you get currents pushing against each other at the anode of the vacuum tube, and then you start hearing that starts causing discontinuities and cracking and collision, and that particularly happens as you start to get the tune of the primary parallel resonant mode starts to get closer to the fundamental series resonant mode of the secondary coil. There is, for smooth running, there is better to have a misalignment there. We're running at about between 2.65 and 2.7 megacycles currently. The fundamental series resonant mode, when coupled with the primary, is around about 3.2 megacycles. The coil, secondary coil on its own, is designed initially for the 80 meter amateur band at around about 3.5 megacycles. Okay, so I'm first of all just going to do the same run as I've done before. I'm going to turn the lights down. There we go. Just check the camera, make sure we can see that. Yeah. Alright, so turn on the supply, bring the remote control. Okay, so the moment I turn on, a very slight breakout there. We have a look at the display. We're running at about 2.65 megacycles, and the output is from the power supply, tube supply, is DC with some feature ripple at around about 2.5. I'd say the average for that line there is about 2.5 to 2.8 kilovolts. No, sorry, times 2. So that would be about 2 divisions, 2.2 divisions times 2 kilovolts, about 4.4 to 4.5 kilovolts out of the back. So we're just going to go run as before. So no change, the experiment at 400 watts. Just got the right up, nice and smooth, 2.3 kilowatts. And we've got all the same fractal fern discharge detail that we had before. No change, no variation to the circuit. Good. Just going to wind that down. Now what I'm going to do is I'm going to change the tuning first of all. So first of all I'm going to tune down until we can't get a breakout anymore. I'm going to keep the power down whilst we tune, just to make sure errors. Let me just adjust this level slightly so the frequency displays. So 2 points. Just adjust a little bit here. So it goes across the zero crossing. That keeps the frequency stable. So at the moment, 2.65 megacycles. So I'm going to wind down in frequency. 2.6, 2.55, 2.45. Now let's bring up the power. Obviously it's smaller, we're further away from the resonant frequency of the secondary, but the form of the discharge is still the same. 2.45 megacycles, let's just check that. Yes, around about 2.45, and we've still got the fractal fern discharge, only smaller. We can push about 1.6 kilowatts through the system. Okay, so I'm going to bring it down, we'll see if we can go down any lower. Just see where we've got to. Upper range. The envelope of the frequency makes it difficult for us to measure. Envelope of the current. I would guess we're down about 2.3 megacycles. Go up again, and we can see the fractal fern is still there, but it's very small. We're getting further and further away from the resonant frequency of the secondary coil. If we go much lower, it's not going to oscillate. Primary will start getting quite hot. Try going a little bit lower. 2.17 megacycles. We come up in power. Very small now. No essential change in the nature of the discharge. 2.16 megacycles. Sugar out a little bit more. Really, that's better. Okay, so we're going to come up again in frequency. That's about as low as we can really go on this system. The power supply is just going to start pushing harder and harder, but we're going to get less and less discharge as the further and further in frequency we go away. Okay, I've given a little time for the primary coil to cool down. The problem with running the system quite far from tune when you're running in CW is the primary will consume more and more current for a much smaller discharge. So even to get a discharge down around about 2.1 megacycles, about 2.17 megacycles, and we were having to put over a kilowatt in even to get just the smallest discharge. That's the difficulty of running far from resonance. So, and that means it consumes more current, and as a result the primary gets hotter much more quickly. Obviously we could improve that by using a pulsed system, for example on the cathode, to put a line circuit synchronized pulse system, but I didn't want to introduce any additional complexities in this experiment, but to keep it actually rather straightforward, so we can get a clear view of what configuration and setup parameters are lead us to the Wheelwork of nature type experiment, and will have an impact on the fractal fern discharge. So I've reset the tune back to the primary tuning capacitor at 231, around about 231 picofarad, and if we just check now, turn it on, bring up the power a little, it's about 2.65. About 2.65 megacycles, which is where we started. And once again, we're back to the same form of discharge. 2.27 kilowatts going in, it's full power. Good. So I'm going to bring it down and I'm going to go up in frequency. So I'm going to wind it the other way, raise our frequency, so bring it up a little bit first of all. Go down there, that's it, it's better, let me go up. 2.77 megacycles, still got the fern. A bit more, 2.9, 2.88, 2.9 megacycles, still got the fern, 400 watts, starting to get some crackling there. The strong oscillatory currents coupling back into the primary, pushing against the tube. A bit more, go up. We'll obviously start reaching instability, where we're going to flip over to the upper parallel resonant frequency. Currently we're on the lower. Still got the fern there. Let's see if I can just get this a bit better. Was 3 megacycles. We're very close to flipping to the upper. A bit more, a bit higher frequency. 400 watts. Much smaller fern now. Still the same form, that fractal fern discharge, even at higher frequency. We've flipped onto the 3.5, 3.6 megacycles, so we're actually running on the upper parallel resonant mode now, and we've stopped. No, that doesn't look like that will oscillate. There. Okay, so we're going to wind down a little bit. I can try winding up much further, see if we get anything. No, we can't get that to start oscillating. So I'm going to bring it down a bit so we can start it again. Okay, so I've allowed the system to cool again a little bit, and what actually happened there is we actually went up to such high frequency in the upper parallel mode, up almost to 4 megacycles, that there was a reflection back off of the coil system, and that blew one of the protection fuses on the output of the transformers in the plate supply. That is designed to protect from the system suddenly stop oscillating for whatever reason, and then up, when you've got it turned up at high power, it suddenly starts oscillating again. There's a big surge of current out of the plate supply, and that I use 1 amp fuses at the output of the secondary of the transformers. That adequately protects the rectifiers. You can increase that to up to 5 amps in the plate supply, but there's no need with the. And I find that the 1 amp fuse actually gives a really good protection both to the coil system and to the plate supply. So I've wound down again. So just to recap, with the tuning, we went from this central point, about the optimum running point, which is 2.65 to 2.7 megacycles. We tuned all the way down to 2.17 megacycles, to the point where it became very difficult to get it to oscillate and discharge, and we were having to put a lot of power in to the primary circuit without starting a discharge, and of course that also generates a lot of heat very quickly. So we went all the way down to 2.1 megacycles, 2.17 megacycles, where we were able to make the discharge. Then we could see that the nature of the fern, or the fractal fern, was still there. So tuning from 2.65 down to 2.17 did not change the nature of the discharge. We then brought it back to 2.65, and we went progressively upwards up to about 2.9 megacycles on the lower parallel resonant mode without any change. And then it flipped over to the upper parallel resonant mode around about 3.3, 3.4 megacycles. We continued up to around 4 megacycles, where the system could not oscillate anymore. Where it stopped oscillating and started oscillating again, there was a surge of current out of the plate supply, and our protection fuse on the output of the transformers blew. So I've now replaced that. I've wound us back to around a tuning primary capacitance of about 231.4, around about 231.4 picofarads. That brings us back to 2.65 to 2.7 megacycles. So we'll just check that again now. So we turn on, wind up a little, so we still get our discharge. You just trigger this, set the trigger in again. There we go. 2.65, 2.66, 2.67. Right up again, right up to just over 2 kilowatts. A fractal fern discharge, nice and stable. Good. Okay, so that was a variation of tuning across the possible drivable range of this coil system with this coil. So what I'm going to do now is I'm going to remove the blocking capacitor at the back. That's the 25 kilovolt, 25 nanofarad pulse capacitor that we've got there, acting as a blocking tank capacitor. I'm going to exchange that for 30 microfarad, 8 kilovolt. So that's, let me just bring those into the picture so we can see them. That's these two. Okay, so quite large capacitors, they store a lot of energy. Let's bring them into the picture. Here we are. So those are going to be replaced now onto the tank circuit. Okay, so I've replaced those capacitors. The 30 microfarad blocking capacitor. That's two 60 microfarad 4 kilovolts in series to make a 30 microfarad 8 kilovolt. And I've connected those at the back. Now, I haven't turned the system on yet, but we watched the charging up even with a very small current when I first turn on. Okay, charged up around, obviously a cleaner, and it's up around about, again, 4.4. Not oscillating yet, let's bring it, start it oscillating. Okay, there we are, oscillating. Let's try and Okay, so winding up is the fractal fern. Right up, 2.1 kilowatts. Same fractal fern discharge as before. Our power, 1 kilowatt. Again, 1 kilowatt. 5 and 2.1 kilowatts maximum output. Good. Okay, so the variation, so we see that this is still charged up. A lot of energy stored in those capacitors. We have a discharge circuit that also can cause oscilloscope restart, but is now discharged. Let's check that again. Okay, good. Okay, so the variation with the much larger blocking tank capacitors didn't make a difference to the discharge. The current waveform out of the generator through the primary through the tube, essentially the same form. So putting those larger tank capacitors doesn't make a difference. What we're going to do now is I'm going to change the nature of the output of the generator. So I'm going to remove the bridge rectifiers. I'm going to connect just the raw output, so that's just the raw output of the transformers directly out. No blocking capacitor. I'm going to take the capacitors away and we're just going to drive it raw output directly to the coil system. Keep the tune the same at the primary tuning capacitor of 230, around about 231 picofarads, and the oscillation frequency we would expect to remain very similar. Okay, so I'm just going to do that and then we'll have another run. I've changed the setup configuration of the plate supply. I've changed the jumpers internally to just the raw output of the transformers, so no bridge rectifier. There is no blocking capacitor connected at the back. I've just removed that, and so we're going to give it another run. So we are still tuned at the optimum position for the coil system, around about 2.65 megacycles. We turn on, check the frequency. Yes, about 2.65. Obviously now we've got a slightly different envelope at the potential output of the generator. We'll wind up until we get a discharge. There we go. Full power, 2 kilowatts. Frequency staying the same. No change in the nature of the discharge, the fractal fern discharge. This was a raw output with no bridge rectifier. Wind down the power a little bit. .2 kilowatts, running stably, sitting at 2.65 megacycles. Good. Okay, so that was the raw output from the generator. That again didn't make any difference to the nature of the discharge. Okay, so the next, let me look at the next variation. that is now going to be, I'm going to put the bridge rectifier back into the system with the blocking capacitor. That's what I consider to be the basic setup, the best forward pressure on the coil system. And then we're going to put a top load onto the system and see what differences that makes. Okay, so let me just reconfigure that and then we'll make another run. Okay, so I've placed a toroid, small toroid, top load, at the top end of the secondary coil. I've also added a breakout point here. We want to generate a discharge rather than focus on accumulating a lot of energy. Without a breakout, this will act as an accumulator. It will accumulate a fair amount of energy. That energy can then obviously get reflected back and back down into the power supply without a breakout. So we put a breakout there to ensure that we get a discharge load at the top end. Obviously the frequency is now going to change. We'll see by how much that changes, and then we'll see the nature of the discharge. So otherwise everything is still the same. So it's bridge rectified with the 25 nanofarad blocking capacitor at the output of the plate supply. So I'll just turn down the lights, just check everything's coming out. Okay, good. So first of all we're going to do some tuning. So let's just turn on at low first of all, just check that comes out. Okay, so that is now 2.34 megacycles. So I'm going to tune simply by the size of discharge. I'm just adjusting the vacuum variable capacitor, looking at the small discharge at the top. So about there, lower parallel resonant mode, that is at 2.37 megacycles. Reasonably similar current waveform that we had before. We're going to go up in power now. So we can start to hear the spitting sound because of the pushback. That's the high currents coupling back through into the primary, pushing hard against the tube. So we need to move the tune point slightly further away from the series resonant frequency. So we're just going to do that. Bring it down slightly. So that brings it down to 2.32 from 2.37. Go up again. Less cracking. Still a little bit. So we'll just go down a little bit further. Discharge gets slightly smaller as we move further away. 2.28. Right up now, no cracking, 2.5 kilowatts. The nature of the fractal fern discharge is essentially the same. No real variation with the top load. Running at 1.7 kilowatts, a bit more, it's full, 2.58. Wind down a little bit, 1 kilowatt. There. The nature of the fractal fern discharge is still the same. Top load didn't change. The underlying nature of that discharge. Stable 2.28 megacycles. Nice and stable. Sound is good. 2.57 kilowatts. down. Okay. And off. Okay, so adding a toroid to the top also doesn't change the nature of the discharge and the form of it. It changed the frequency, as you would expect. By adding a top load, frequency is going to go down because we are loading the secondary coil with a predominantly capacitive top load. Moving down from without it was nominally for the secondary coil it would have been around about 3.1, 3.2 megacycles. When coupled with the primary, the lower parallel resonant mode was being driven at 2.65 megacycles. With the top load on, the optimum lower parallel resonant mode had moved down to about 2.28, 2.3 megacycles, which means that the secondary coil would have probably, its series fundamental resonant mode would have also come down to somewhere around about 2.75 megacycles. So a frequency variation, but it didn't make a difference to the discharge. Okay, so the final variation that I'm going to make in this video is I'm going to put the dual 833C tube supply in and fundamentally drive them with a different set of tubes. And we see, instead of the GU5B, and we see if that makes a difference. Okay, so what I've done now is I've turned off the GU5B in the coil system. So this is now wound down, it's off. We're still using this side, so the primary, the secondary and the variable vacuum tuning capacitor in the primary circuit. And now I've added the tube power supply heater grid screen unit, and I've got the dual 833C power triode board attached to the top. Again, it is configured with the pickup coil to form a series feedback Class C Armstrong oscillator. These an 833C takes 10 volts, 10 amps heater, so we've got two in parallel, and we're at 20.2 amps there. Just adjust slightly. 20 amps. 20 amps at just slightly over 11 volts. That will be about 10.5 actually at the tube terminals themselves. Otherwise, everything else is the same. The anode supply is configured in the same way. It still has the bridge rectifier in and the 25 nanofarad blocking capacitor at the back, so that remains the same. So what we're going to do now is we're going to again wind up, do a run, look at the tuning, and also look at the nature of the discharge that we get in both at the lower parallel resonant frequency and at the upper parallel resonant frequency. So first of all, just turn on, bring up just a little bit of the discharge. We're currently tuned at the lower parallel resonant frequency. Let me just wind up a little bit so we can see the frequencies of 2.75. I'm going to wind down a little bit. It's going to get smaller, smaller. Let's see where we are. 2. A bit unstable. Just adjust a bit. Around about 2.3. Not much discharge even if I wind up. So I'm going to tune in now to the optimum point for the lower parallel frequency. Discharge getting larger. It's better. 2.76 megacycles. Fractal fern discharge using the 833Cs. 2.9 megacycles. Fractal fern discharge looks almost identical as before. 1.5 kilowatts. Nice pair of tubes these. 1 kilowatts. 2 kilowatts. Very good. Down to 1. Down. 2.9 megacycles driving those. So turn off. Just check the. Just let the primary cool a little bit. We're still running in CW, but they're running at the lower parallel resonant frequency using a different tube drive. The fractal fern discharge is of the same nature and the same form. It doesn't appear outwardly, it doesn't appear distinctly different from when driving with a single GU5B. What we're going to do is we're going to wind up to the upper parallel resonant frequency. We can do that. These pair of tubes here are quite flexible, and rather than a single tube, and they continue oscillation quite well as you make the jump across from the lower parallel resonant frequency to the upper. Let me just check here. Okay, so let's bring oscillation back on again. Okay, so 2.9 megacycles. I'm going to keep it's about 350 watts. We'll just check it again. There's the discharge. I'm going to wind it back down, and I'm going to keep winding up, pushing back there, very close to the series. The parallel mode now is very close to the series resonant mode. Now we're at 3.8 megacycles. We've jumped over to the upper parallel mode. Just adjust a little. 3.8 megacycles. Let's get a little bit more. So we can measure it. 3.8. Now if I wind up the power, 1 kilowatt. 3.8 megacycles, 2 kilowatts. Now we notice here we still have the fractal fern discharge, but the detail is closer, more curved. So we still have the fractal fern discharge, but the detail is somewhat different. 2 kilowatts, running at 3.8, 3.9 megacycles. We're just going to give a chance for everything to cool down. Just make sure we're discharged. Yeah, not very difficult for a pair of those tubes to push at 2 kilowatts. Okay, so whilst that cools a little, they're up at the higher frequency, the upper parallel resonant mode, around about 3.8 megacycles. We still had the fractal fern, but it was tighter. So the curves were tighter, the whole structure was more rounded. So although the fundamental nature of the type of discharge hadn't changed, some of the detail of its structure had changed. So what I'm going to do is I'm going to set up the camera at this frequency. I'm going to keep it there. I'm going to bring the camera in closer to the discharge so we can get some of that, we can get a run on the film. Okay, so I've repositioned the camera. I'm looking directly on at the top end of the secondary coil. I'm going to start that run again. So this is at 3.9 megacycles, the upper parallel resonant mode, and we see how the discharge looks. Okay, so wind up, it's about 250 watts. About 1 kilowatt. Kilowatts. Stable. 3.8 megacycles. We see that the fractal fern is tight, the curves are tighter, there's more emergence of secondary streamers. I think 2 kilowatts sustained. Wind back down. 1 kilowatt. $250 watts. Back up again. 500 watts. 1 kilowatt. 2 kilowatts. That's 1 kilowatt. 500 watts. 250. Back up again. 1 kilowatt. 3.8 megacycles, the upper parallel resonant frequency, 1 kilowatt output, 4.4 kilowatt plate supply, nice and stable. Good. Okay, so I'll move the camera back out again. Just bring the camera back over. Put it back on the experiment. Okay. So there with the dual 833Cs we were able to move more stably. We've got 2 tubes in parallel, more stably between the lower parallel and upper parallel resonant frequency. In both of those positions we were still got a fractal fern discharge, although the tightness of the geometry of it appeared different. So some variation by being able to operate at that higher frequency. That may not be a product actually of the tubes, but in actual fact we could run stably at a higher frequency where we weren't able to do that with the GU5B. With a pair of GU5Bs that may well be possible. Okay, that really concludes this total video experiment. So we went through the variations. We actually found that the variations that we've made so far don't actually change the fundamental nature of the fractal fern discharge. The principles underlying going on there as part of the wheelwork of nature, they are defined, and it seems they are almost entirely defined by the nature of the coil, secondary coil itself, the frequency at which it operates, and in the write-up we're going to have a look in more detail at that quality of frequency and what that actually means in terms of a quality of vibration, and what that can actually tell us about the real work of nature. Great, that's the real work of nature, fractal fern discharge.